Hello everyone, my name is Willem Zohar, and on behalf of my collaborators, I'll be presenting our work on reducing the size of knowledge-based indices using dimensionality and precision reduction. Historically, there has been a large focus on non-parametric models. Those are not models which don't have any parameters, but rather they don't have any fixed amount of parameters. This approach is particularly suited for tasks such as question answering, because the knowledge is retrieved from a database or knowledge base in general. Opposed to that are models which store their knowledge in parameters, such as pre-trained language models. This is something from the last 5 years, but as you all know, they became largely adopted in the NLP community. These models, however, have some serious flaws, such as they become outdated very quickly, they provide very little explainability, and they do poorly on unseen phenomena. So there are these two groups of approaches utilizing non-parametric and parametric models. But recently there has been an emergence of the combination of these approaches. The way they work is that they retrieve something from a knowledge base, which I use as an umbrella term for any persistent storage. This retrieved item, which I call the artifact, is then merged in the computation of a parametric model. For example, in question answering, you get the query, you use the query to get relevant documents, you process them somehow, and then you feed them together with the query to fine-tune Roberta or other parametric model. And finally, getting to this graph, we can recreate what's happening in this model. We start with the query, then for example compute an embedding of it, or use df/idf. Then we give it to the retriever, which does maximum similarity search over a knowledge base. Then the aggregator can rerun them and concatenate them, and we can get something called an artifact. This is then fused into the model, for example in the form of priming, and finally we get the output. What's interesting is that this also works for other tasks, such as fact-checking, knowledge-based enhanced language modeling, knowledge of a dialogue, and so on. There are some differences, for example, the source of the knowledge base, the key value types, the specificity of the artifact, or most importantly, the way the artifacts are fused into the model. For example, priming is an early fusion, but essentially they share the same architecture, and it's good to keep this in mind because improvements for models for one task can also transfer to others. This formalism also allows us to ask questions such as how do different fusion mechanisms affect the model computation. The index of Text Wikipedia 2019 is about 50 million vectors, which is 160 gigabytes if you are using 768 dimensional vectors. This won't fit onto your local GPU and probably also your cluster GPU. If you want to use the whole index, you have to run it on CPU RAM memory and need about 1 terabyte of it, because you may be duplicating it a few times and doing stuff with it. And this creates large barrier and, more importantly, makes experimenting with large knowledge bases unpleasant because your experiment turnover time is not a few hours but a few days. Because the most common operation to do on a knowledge base is retrieval, we focus on minimizing its size while trying to preserve the retrieval performance. In retrieval, what we are usually trying to do is to find documents related to a specific query. The relevancy needs to be a function that takes a query and a document and produces a number. The higher the number, the more relevant the document is to the query. What has been shown to work well was to compute embeddings of the query and the document, and then use some mathematical functions for vector similarity, such as the inner product. This is shown on the second line and empirically works well, because many vector similarity functions are decomposable and run very fast. The knowledge base index is these pre-computed document vectors, and the typical dimensionality is 768. The next step is to use dimension reduction functions R, and again the same vector similarity. This would make the computation of relevancies faster and also reduce the knowledge base index size. How well this works is the topic of this paper. There are multiple models that represent function f, and specifically what we use is either the CLS token representation or the average token representation of the last layer. This similarity function is commonly either an inner product or the L2 distance, and depending on what we use together with the model, we get different results. We can see in the solid bars, for example, that vanilla bird is not very useful for similarity, which is one of the conclusions of the sentence bird paper. The best is DPR with CLS representation, which isn't really surprising because that's what it was trained to be, to provide a good similarity function. An important aspect is pre-processing, specifically centering and normalizing the vectors. If we do that, not only do we most often than not get a better performance, but also the ordering given by the inner product and the L2 distance becomes the same. The first dimension reduction method is random dimension dropping. Here we simply randomly choose dimensions to drop and we keep the rest. There are standard methods for random projections, such as sparse and Gaussian random projections, but they work less well. A more sophisticated approach is to select dimensions that contribute the least to retrieval, and this we call the greedy dimension dropping, which stops all other curves. For this method, we center and normalize before and after the dimension reduction. While greedy dimension dropping is the best, most of these methods saturate very quickly and reach closely to the uncompressed performance, which is the gray horizontal line. While the performance of the sparse projection serves as a baseline, we naturally examined also other methods, namely PCA and gradient optimized autoencoder. This graph shows the PCA and a simple two-layer autoencoder with various preprocessings. The red lines are retrieval using L to distance and blue lines retrieval using the inner product. Both of these methods are very sensitive to preprocessing. For PCA, that's clear. The preprocessing is a vital part of the algorithm. For the autoencoder, it becomes much less stable, and while it's a bit better than the PCA, both saturate very quickly at around 128 dimensions. We train the models either on just the document embeddings, square embeddings, or both, and see that they differ quite a bit. They are represented as a different line style. Solid is for documents, dotted is for queries, and dashed for both. We can observe that training on queries is better when we are not doing any preprocessing. The reason is that queries are already more centered. This stops being an issue if you do the preprocessing. We can also see that the reconstruction loss is not the best indicator of the retrieval performance. That's something which I consider to be a major flaw of most of these approaches. It is possible to construct an example of a projection matrix that has zero reconstruction loss, but does not work for retrieval at all. There are methods for manifold or distance learning, but they just didn't work, mostly because the common methods, such as t-SNE or UMAP, are usually used for visualization, and they work very well with 2D or 3D, but we can't ask them to construct a new 100-dimensional space. We tried proposing our own method for manifold or distance learning that was based on contrastive learning and learning the distances of the original space. This is a loss more closely related to the retrieval task, but unfortunately the intermediate results were at best comparable to the baselines. That said, I believe that this is still a remnant area of future research. Another standard way to reduce the size of the data is to simply use lower numbered precision. This can also be combined with the dimension reduction methods such as PCA. Then it becomes a trade-off between the compression ratio and the performance loss. We find that 8-bit precision is almost as good as 32-bit precision, and we can combine that with PCA to 128 dimensions, and get 24-fold compression with 92% of the original performance. We also use just 1 bit per dimension. Simply, if the number is larger than 0, we set it to 1, and if it's lower than 0, we set it to 0. This has much worse performance, but also gives, for example, 100-fold compression when combined with PCA. Here we get 75% of the original performance. Here we have a big summary of the methods, just to show that it really is a trade-off between the compression ratio and the original uncompressed performance. As mentioned before, PCA are slightly worse than the autoencoders. Notable are the combinations of PCA and the precision reduction. Important is also the effect of post-processing, that is after the dimensional reduction. In most cases, centering and normalizing the data again only helps. For the PCA, we also use a few tricks such as rescaling down the top 5 dimensions so that they don't dominate the vector space. Also for the autoencoder, we consider several models. The first one is just one linear encoder and decoder layer. Then 3 encoder and 3 decoder layers, that's the full model. And finally 3 encoder and 1 decoder layer called the shallow decoder. The idea behind this is that we want the latent space given by the bottleneck layer to be as close to the original as possible, and we achieve this by having just one decoding or unwrapping operation. Another way to achieve this is to regularize the autoencoder, and indeed this helps a bit. For all methods, we can also see that preprocessing and post-processing is vital. We also explored some other properties of the methods. For example, how much data do we need to fit the PCA and the autoencoder? That's shown on the left figure with the solid lines. Right, and surprisingly, PCA needs just about 1000 documents because it only estimates the covariance matrix. The autoencoder is much less stable and needs a lot more data. I was also curious what happens if we add some random documents which are not relevant to any query. This means that they can only worsen the performance. That's shown with the dashed lines in the figure. The gray dashed lines is the uncompressed performance, and if we add more documents, then it obviously goes down with a certain slope. Please note that the x-axis is log scaled. If we add more irrelevant documents and then run the dimension reduction, then the performance deteriorates more quickly, which is a caveat of these unsupervised dimension reduction approaches. Next is just a small sanity check of the performance. Every hotbot QA question requires exactly 2 relevant documents to be retrieved. For example, a question may be, is person A older than person B? And for this we need to retrieve spans that talk about the person A and person B. What I was worried about was that even though the numeric performance was okay, what could be happening is that we stopped retrieving both documents and just retrieved one document. But as the figure on the right shows, that's not the case because the diagonal is still dominating the first row. A semi-interesting finding is that the subplots look similar even though in the first case we use PCA for dimension reduction and in the other we use 1 bit per dimension. That means that the introduced error by the dimension reduction is random and not systematic. Finally, I also explored some implementations of PCA and Autoencoder and how fast they train and run the inference, and the recommendation is to use PCA with PyTorch, and if you want to run the Autoencoder, then only if you have a GPU. The main takeaways are to do the pre-processing and post-processing properly, that is centering and normalization. For the methods, PCA is a quick and good enough solution that requires very little data, is stable, and can easily be combined with precision reduction. For the future work, I would like to see more progress in fast distance or manifold learning for high-dimensional data, because as we saw, the methods relying on reconstruction laws such as the PCA and the autoencoder have no theoretical guarantees. Thank you everyone for listening to my presentation, and please reach out to me if you have any questions or need some clarifications. Bye!